Hi, in this video we will be learning binary search algorithm, which is faster algorithm than linear search. Below I gave an array of size 15, and this array we will try to find the key element 18. But in order to use binary search algorithm, our array should be in sorted order, and our array is in descending order. Why do they call this algorithm as binary? Because we are starting to search in the middle of the array, and we are splitting the array into two parts until we find the key element. If we use linear search in this example, we would make 5 comparisons in total to find 18. This will be the first, the second, third, fourth, and the fifth comparison. In linear search, we make 5 comparisons to find the key element 18. But in our example, by using binary search, we will make less comparison than linear search. In this method, we need 3 index variables. These are low, high, and middle. And middle will be equal to high plus low divided by 2. So what about low and high? Initially, low will be pointing the 0th index, and the high will be pointing the last index. Low will point this index, and the high will point the last index. Now we need a table to track our variables high, low, and middle. At first, low is equals to 0, high equals to 14, and the middle is 14 plus 0 divided by 2, which is 7. And now the mid variable will point this index, the 7th index. And we need to compare this variable, which is 27, with our key element, which is 18. And 18 is smaller than 27. So we need to look to the left side of the mid variable. Because this array is sorted in descending order, 18 should be on the left side of the mid. So we need to check this side of this array. And in order to search to left side of the array, we need to update our variables. And low will be the same, but the high variable should be mid minus 1, which is 6th index. We are not looking to the 7th index because we already compared the 7th index to our key element. So we need to update the high variable with mid minus 1, which is 6. And our middle variable will become 6 plus 0 divided by 2, which is 3. And now the high variable will point 6 and the mid will point 3. Now low points to the same index, high points to the 6th index, and the mid points to 3rd index. And again, we repeat the same process. We compare the 3rd index, which contains 15, with our key element 18. And 18 this time greater than 15, so we need to check the right side of the array, the right side of the mid variable. So this time we need to update the low variable with mid plus 1. Low will be 4, high will be the same, 6, and the middle will be 6 plus 4 divided by 2, which is 5. And now low points to 4 and the mid points to 5. And this time we again check our key element with the 5th index, which contains 21. And this time 18 is smaller than 21, so we need to check the left side of the mid. So we need to update our variables again, and the low will be same. The low will be 4, but high will become mid minus 1, which is 4. And the middle will be 4 plus 4 divided by 2, which is 4. And this time low points 4th index, high points to same index, and the mid points to same index. And now we check the 4th index with our key element, which is 18, and we found our key element at 4th index. And this is called successful search. And in this successful search, we only made 1, 2, 3, 4 comparison. So let's make another successful search, and this time we try to find 34. Now our key element is 34, And at first, at initial step, the low will always point to the low always points to the 0th index, and low which is equal to 0, and the high will point to the last index, which is 14. And the middle is the same, low plus high divided by 2, which is 7. Mid points to the 7th index. And our key element is 34, and at 7th index we have 27, and our key element 34 is greater than 27, so we need to check this side of our array. So we need to update our low variable to mid plus 1. Mid now points to 7, and the low becomes mid plus 1, and low becomes 8, high is the same, and the middle becomes 8 plus 14 divided by 2, which is 11. And this time low points to 8th index, and the middle variable points to the 11th index. And the middle variable shows the 11th index, contains 37, and our key element 34 is smaller than 37, so we need to check the left side of the middle variable. So high variable will come here, low will be the same, and low still 8, high becomes middle minus 1, which is 11 minus 1, 10, and the middle becomes 8 plus 10 divided by 2, 9. And this time high shows the 10th index, and the middle shows the 9th index. And this time at 9th index we have 33, and our key element 34 is greater than 33, so we need to search the right side of the mid variable. So this time we need to update our low variable, and low will become mid plus 1, and mid now 9, and the low becomes 10, high will be the same 10, and middle will be 10 plus 10 divided by 2, which is 10. And now this time 10th index, low, high, and middle. And this time middle variable points to the 10th index, which contains 34, which equals to our key element. And in this search we made 1, 2, 3, 4 comparison. So as our last example, let's make an unsuccessful search. This time our key element will be 25, and 25 does not exist in our array. And at initial step, low will point to the 0, and the high variable will point to the 14th index, and the middle will point to the 7th index. At 7 we have 27, and the key element 25 is smaller than 27, so we need to search this side of the array, and we need to update our high variable as middle minus 1. Low will be the same, 0, high will be 7 minus 1, 6, and the middle becomes 6 divided by 2, 3. And now mid points to the 3rd index, which contains 15, and our key element 25 is larger than 15, so we need to check the right side of the table. So we need to update our low variable as mid plus 1, and the low becomes 3 plus 1, 4, high will be the same, 6, and the middle will become 6 plus 4 divided by 2, which is 5. Low, high, and mid. And this time mid points to 5th index, which contains 21, and our key element 25 is larger than 21, so we need to check the right side of the table. So we need to update our low variable. So low becomes mid plus 1, 5 plus 1, 6, high will be the same, 6, and the middle will become 6. And now all three variables points to the same index, low, mid, and high. But mid points to the 6th index, which contains 24, doesn't equal to our key element 25. So 25 is larger than 24, so we need to check the right side of the mid. So we need to update our low variable as mid plus 1. And this time low becomes 6 plus 1, 7. High will be the same, 6. And this time we don't need to check our middle element, because in this example our low variable becomes larger than high variable. So we learned that if low becomes larger than high, we stop the search, because in our example high will be always at the right side of the table and low will be always at the left side of the table. So we learned that in our binary search algorithm, low index cannot be larger than high, because high variable will be at the right side of the table and the low will be always at the left side of the table. After making these observations, let's write our binary search algorithm. Let's call our function as binary search, and there will be 3 variables: low, high, and the key. At first, we need to find the value of middle, which is low plus high divided by 2. Then if a of mid, a represents the name of this array, a of mid if equals to our key element, we will just return mid. Else, if our key element smaller than a of mid, we need to check the left side of our table. So high variable should be updated as mid minus 1. Else, we need to check the right side of the table. Then we need to update our low variable as mid plus 1. And we need to make these instructions while low smaller than h. And outside of our while body, we need to return simply minus 1 to say that we couldn't find the key element. If we find the element in the while loop, we will just return the mid. But if we can't find the key element in our while loop, we will skip this while loop from this point and we will just return minus 1 in order to tell the user that we couldn't find the key. And now we can use Xcode to write our code and check if it works. At first, I'm going to include IOStream library. Then I will use namespace std, and let's define our main function. Let's create our array, and I will call this array as numbers, and it will contain 15 elements. And our elements will be the same. In our example, I will use this array and I will call our function binary search numbers. The name of the array will be sent as a parameter, and the key element, which is 18, and the length of our array, which is 15. And this array and this function will return an integer value, and I will call it as index. And if the index does not equals to minus 1, which means that we found our key element, I will just print else not found. So let's create our binary search algorithm. It will just return integer value and its name will be binary search. And we need to create an pointer and the key and the length. I will create 3 variables: low, high, and middle. Low initially will be 0, and the high will be initially length minus 1. And while low smaller than high, at first we need to calculate the middle variable, which is low plus high divided by 2. If key equals to a of middle, we will just return the middle index. Else, if key smaller than a of middle, we need to check the left side of the table. So we need to update our high variable as middle minus 1. Else, we need to check the right side of the middle variable, and which is low equals to middle plus 1. And outside of the while loop, we will just return -1 to tell the user that we couldn't find the element. Let's check our element. Let's check our code. Okay, we are searching 18 and we need to find the 18 at 0, 1, 2, 3, 4th index. Yes, we found the 18 at index 4. Let's search 34. And it is located at 9th index. It's correct. And let's make an unsuccessful search. Let's search 25. We need to see not found message. Yes, it's correct. And the time complexity of binary search algorithm will be, we have two possibilities. First, we can find the element in the first comparison, and which will be called as best case, and the time complexity of the base case will be constant time, which is order 1, and the worst case will be log n, which is smaller than order n, and this order n represents the time complexity of linear search. Yes, this is the end of our tutorial, and the next time I will be telling the linked list, the creation of linked list, displaying of the elements of the linked list, and later I will try to explain the stack, queues, and the binary search trees, and the pre-order, in-order traversals, and the graphs in the upcoming videos. I hope you liked the video. See you next time.